share with us. He was telling us about a rather interesting collaborator in court that his chief, James Schwan, whose biography is just too big. With that, Pramod is going to tell us about the optimal mechanism in differential privacy.
Thank you, Balaji, and it's always a pleasure to be back at ISL, and thank you for coming here. So this talk is on privacy, and which is somewhat a new topic to me. And it took me some time to also just convince myself and think about it. Should I work in this? And some of you may know me, and I work on somewhat more boring and things like wireless and so forth. It's very clear engineering connotations. So I spent some time thinking about it. So I'll partly spend the talk, maybe the first 10 minutes or something, just to share my thought process, get the motivation going. So privacy, as the word says, private, is essentially individual. It could be many things that's individual, financial status, health, whatever. And the point, I guess, of its importance is that other people knowing this may lead to some discrimination. And to the extent the person feels unhappy that somebody else knows this and destroys his pursuit to, I guess, the right of pursuing happiness, I guess it's a fundamental right. To that extent, it's some kind of important. Like I said, I need to make sure it's important for me to think about. So it's individual, but I think what I want to say is it's very cultural. I grew up in this part of the world, and I'm still not fully sure what this privacy means. It's not, so it's a hard thing actually. It's not quite, it doesn't sort of make sense. It's a cultural thing. In this part of the world is where I lived my other half of my life, and I'm getting to a bit more feel. And I think in this place I visited, but it's more, privacy makes a lot more sense. And one way to see it is through Google's eyes, and Google has way more problems here than, let's say, here. Way more problems. Yeah, every country look at Google's having problems. This is France, Italy, Germany, everywhere. So it's cultural. So it's personal, and then it's cultural. And so the thing is, privacy is different from secrecy, in the sense that you actually want to reveal information. It's just that you don't want to do it too much. You don't want to overdo it. Despite, I guess the point, is that it happens inadvertently. You didn't mean to do it, but it happens. And broadly, it happens in two ways. Once individuals themselves go out of their way and reveal what, maybe they reveal more than they should have. That's one thing that happens. The other thing that happens is that you really didn't have a choice. You're pretty conservative in the sense of being careful and so forth, but somebody else did it. And you didn't really have any control over what happened. Both are interesting, and the formulations that I talk about will handle both of these things. So both of them are important. There's plenty of culture, so if I want to think of local privacy, so there's plenty of cultural exhortation for people to, keep quiet and not over-reveal what they're saying. But, there's plenty of incentive here. All these are sort of billions of dollars business built on people saying more than they should. Plenty of incentives all over the place. So that's from the individual side. From the institutional side, well, we don't really have control. I mean, there's governments, there's universities, hospitals. Your census data is publicly available, birth death records, who bought what. So it's all publicly available. You didn't really have any control, or you couldn't really keep it private even if you wanted to. So that's the sort of the challenge. And I think this has been around. Privacy is there as early as sort of human societies. But in the era of big data, it takes a more ominous note. The point, I guess, is that individual revelations are there here and there, but they can be correlated, and they can be tracked in both time and across types, that is images, videos, voice, all kinds of things. So big data gives sort of unusual power. You said something and then maybe nobody heard it or something previously, but now it's just there forever and for everyone. That's what makes it interesting. The point is, these attacks are very strong. So any one data release is potentially very benign. In fact, that's where people have taken care to make sure anonymity is there. But then when you correlate it with something else, which by itself was benign, this is a very powerful attack. And many, many instances of it. In fact, it's hard to think of any data release that has not been led to a breach. It's kind of, it's the other way around. Everything happens. So early on, there was this AOL released this data. This is early when they were still doing the search business and so forth. They released their search data, and so this lady was exposed to the New York Times, de-anonymized, just based on some of her searches. So she had some things, and then there are a couple of just investigations and some other web searches by the reporters, even reporters can do it right there. And this is a more famous one. Netflix released its data for doing recommendation systems. They anonymized users, and they released sort of this table, user ID versus movies up or down, depending on how they're rated. And the idea is that they wanted recommendation systems. And Narayanan and Schmartikov correlated with a public database where people volunteered their ratings for movies and wrote reviews. And this is Internet Movie Database, and you put them together. In the Internet Movie Database, some people identified themselves, and the two things is equal to just match them. So Netflix had released anonymized data, but that's enough to kind of come. And basically they said 4 movies identify user. So this was sort of a bit. This is an example.
Identified means what? That is, Netflix verified that these people were indeed.
There are 2 ways of saying this. Yeah, in this case they were. And also they can win the they're part of a recommendation system contest. So if you really know, if you actually identify who the user is, you go to IMDb, see which other movies.
No, that's just filling the entries.
Right.
So Netflix didn't verify that these users.
I think they did in this case. They accepted it.
Okay.
And Netflix kind of postponed their data, and there was some issue. In fact, they were sued, and there are all kinds of things that happened. And this is, you would think, relatively thing. So this is a more recent one. How about this? This is not a composition attack. Flickr released their data again to build recommendation systems, and they knew, of course, the Netflix story. This is just as of December 2010. So they knew the Flickr, the Netflix debacle. So they knew they were being careful. So they released something, a small subgraph of their existing social graph, and also randomized it and put some noise on it, so just to make sure anonymity is there. Nevertheless, the winning strategy was actually just to de-anonymize. And basically, Arvind Narayanan here told me that, they're not really random graphs. You can just eyeball, and social graphs have a lot of structure on them. So this is just from last year. Again, I'm just saying basically there's too many composition attacks. This is from science just identifying a human genome. This is just AGCT patterns. And they can get their surname. And if you are getting into more conspiracy, then here's this guy. Graduated from Berkeley at the same time I did. And he can go from images to social security numbers. SSN you think is random, but it's not really. And this one is not available now. If you want to try. Okay, so in '93, New Yorker ran this classic cartoon. On the internet, nobody knows you're a dog. And I asked my daughter, what do we do for 2013? And now 2 decades later, definitely the internet knows you're a dog. It also knows more things that it shouldn't. So that's the sort of the privacy era of big data. This is how sort of internet began, and 2 decades later it's different. So the challenge, so it's really a challenge. So when you release information, you don't really have control over what was said in the past, what was in the future, by someone else. So you don't know who knows what said information. And the other aspect of privacy is that it's kind of irreplaceable. Once lost, it's gone. It's like kind of time. It's got a directionality. And it's sort of a burning issue, if you notice. So commercial software, there's efforts to address this both from a commercial perspective and just government gets involved in this. So the fastest growing social network is Snapchat, which is like a video sharing site, image and video sharing, where you send the video. It's like Instagram, but it's the newest one. Snapchat just destroys the image in 10 seconds. When the other person views it, looks at it for 10 seconds, it's just gone. You can't store it. It's kind of addressing this privacy aspect. So there's commercial software, private, you can look at legislation too. So how does one address this? It's really a challenge. And what does one do? And it's kind of a complicated thing. It's already called this cultural, societal, all those things. Every now and then, you think about such a complicated thing, but every now and then you see something and that really brings a moment of clarity, like a beacon of clarity. And I found this in the April New Yorker issue. And this article, one of the articles here in this issue said this. The future of privacy is to just lie. So not say the true thing. And to do it systematically is, of course, to randomize. And the name of the game is how to sort of systematically and efficiently do this. How do you be sort of useful and sort of hide information?
I think it's two issues. At some places you don't want to. When you're trying to, for example, formulate health policy, it's better not be lying. Otherwise, you could be causing very much systematically.
Yeah, so there's definitely a trade-off. So privacy comes at a cost, and the question is to understand at least what the relationship is. And in this talk, we'll try to address sort of a fundamental trade-off. And we'll do it in a certain, somewhat specific context. And let me get this. So usually I used to say that in my talks, slide 3 we would get to symbols and math. But these days I'm getting a bit older, so we're going to get to it in slide 11 and 12. So this is where we are. So here's the setup. So how do we model this situation? The situation is that I don't want, so the other person may know everything. He just shouldn't know what my intention was when I reveal something. So one way to do it is a hypothesis testing formulation. So you release some data. You don't release the whole data D, but maybe you ask a question and you release the answer to that question, like the average salary or something like that. And the attacker is curious to identify what the underlying data, not what the underlying database was, but just to decide which of two databases it is. In particular, D1, D2 differ in only, let's say, one person's information. Then knowing it's D1 or D2 will identify that person, basically. So that's how you kind of figure out, that's the differential aspect of privacy. So just to sort of notice one, not the whole database. This would be in the release setting, data release. And data collection, you would think D1 and D2 are sort of whatever the information that you want to hide. And that's the one that we try to run. So here's how your randomization works. Here's a data set D. A query set could be some kind of a level set. How many people are above some value? And randomize, so you would say the answer. It's sort of a deterministic function of the data. But a randomized mechanism will say something random with some probabilities. Maybe high probability, large probability for the true answer, and less probabilities for the others. So that's kind of what a randomized mechanism will do. And neighboring data sets look like this. They're pretty much the same, except it's got another user missing. And so if he knows it's either this or this, then he knows that C is there. And by looking at the query output answers, you can figure out what that value was. So this would be a model we'll use in this talk. In particular, I'll think of all the outputs as numbers. So in general, you could be releasing more abstract quantities, right? So we talk maybe briefly in one of the slides there. So sort of there's a way to handle that. But for now, we'll just talk of numbers. And so what you release is a true value is a number. What you release is also a number, but it's a random variable. And I'll think of just adding noise. And in particular, if this random variable is different for different data naturally, even the output is different. But if the random variables are somewhat close to each other in some way, then it's hard to infer what D1, whether it was D1 or D2. So that's the point of, and you add noise so that they become that way. So how do you make this happen? There are two types of inference errors, false alarm and misdetection. We understand this. And privacy is about ensuring there's enough error. False alarm and misdetection is above something. So it's kind of the opposite of communication where we are saying, given a noise, we want to minimize false alarm and misdetection probabilities by setting a rule. So this is the opposite. No matter what the rule is, detection rule is, I would like my false alarm and misdetection to be above some thresholds. That's what privacy corresponds to. But I get to decide the noise. So one specific way of enforcing these errors is this setup of what is called differential privacy. It is not quite how it was formulated in the original papers. The original papers formulated more like a fiat, like a law, like a definition, that's it. But this is a more operational way of thinking about it. And there is one parameter, so we'll have minimal notation, but this is a notation here, epsilon, it's an important one. Epsilon controls the privacy level. Loosely speaking, epsilon small is high privacy. That means your false alarm misdetections are pretty large. They only have to be in this region here. And epsilon large means low privacy. So if you want to think of numbers, 0.1 and 10 are some numbers I picked. It's also reasonable. That's the kind of numbers that systems papers, people who do numbers and applications of this area use in the literature. Large means false alarm misdetection can be in a larger area, and of course you probably work somewhere here. So this is the definition of differential privacy, right? So the differential privacy is, like I said, has an operational interpretation, but it's defined as the ratio of the likelihoods. Look at the conditional probabilities on the two D1, D2s, and look at how the random variables, the output random variable, what you send, looks like. So it's the likelihood. Look at the ratio of the likelihoods, and these likelihood ratios should be within the interval. If the ratio is 1, then you'll never distinguish D1 or D2, so the errors are full, like half each. Then it's full error. In general, you allow some interval around 1, the ratio. How the interval is depends on epsilon. Like that's why I said larger epsilon, larger the interval, so less privacy. Smaller epsilon, closer to 0 means it gets close to 1, and now it's really very high privacy. So in particular, this implies this kind of constraint on false alarm misdetections. So this is Joe and Wassel. Okay. So let's just keep this in mind. I mean, I'm thinking, right? I said wireless early on. That's what I used to do. So we used to SNR. So high SNR is good, low SNR bad, but here it's the opposite in some sense. Epsilon small means high privacy. Epsilon large means low privacy, with the reverse of the SNR state. Okay. The key question is how much noise to add. So I said what you send is what you should plus noise. And the answer, I guess, is as little as possible. Nobody wants to add too much noise because then the utility somehow goes away. And really depends on how Q of D looks like, how sensitive it is to two differential data values. If QD1 and QD2 are the same, then you can just release the true answer. There's no noise because you'll never distinguish anyway, whether it's D1 or D2. In general, if D1 and QD1 and QD2 are small, then you kind of also get away with low noise. If QD1 and QD2 are QD1 is very sensitive to what D1 is, then you'll have to add more noise to kind of bring down the sensitivity. In general, so you need this parameter, I guess. You go from the query functions to something on the real line, so I guess you need some kind of Lipskitz continuity. So delta is this. So you look at how different the outputs are for differential values, and you kind of look at the worst case value. See, the point is, I guess I want to do hypothesis testing between D1 and D2, but I don't really know what those D1 and D2 are. I want to do for every data sets which are neighbors, or which differ in only 1%. A classic example would be where the query is like a count, like an integer, and histogram would be an example where sensitivity is 1. That means one person will change the histogram in only one of the bits. Rule of thumb is the more the sensitivity, the more the noise you have to add in general. Okay, here's the state of the art. The state of the art is you take your output number and you add a noise to it. And this noise is two things. I never said when I add noise, I didn't say it should be data independent, right? It could have been. In general, the most natural mechanism would be to do some perturbation of Q. And I'm adding noise. Noise could have been output dependent. But the state of the art is not doing that. It's doing independent. And step 2, furthermore, it's adding a specific type of noise. This exponential random variable, exponential on both sides, so symmetric. 0 mean is kind of natural here because you want to minimize variance or something. So you do 0 mean, but this is the so-called Laplacian random variable. It's a basic tool introduced very early on in the seminal papers of differential privacy, and it's hard to look at one paper of differential privacy which does not sort of use it. It's used, yes?
I have a very basic question. Maybe everyone understood. When you said epsilon is very small, and you also say that the error has to be large and the false alarms have to be large for the privacy to be good. On those two, didn't quite understand. So if epsilon is large, then false alarms and errors could be large.
No,
they're comparing.
No, this is the operational definition. So if you look at this, when epsilon is small, false alarm detection get to be large, forced to be large. Its epsilon is like e to the minus epsilon sitting here.
In the previous diagram where you're showing
Here?
before that, yes.
Yeah.
And you said that in order for the privacy to be good, your false alarms and errors have to be high.
Yeah, that's the kind of true.
Right. And if the epsilon is so low that your false errors and alarms cannot be high.
Epsilon is kind of inversely related to the probability of false alarm and misdetection. So it shows up right here. It shows up in e to the minus epsilon. So that, I mean, this is just notation.
Okay.
I just want to, I just stated that.
Thanks for the clarification. So
yeah, it's just notation there.
I think usually in life, epsilon needs to be small.
Yeah, I know what you mean. And maybe that's one of the reasons I noticed that in machine learning. So this area is mostly people in this area work either in sort of crypto areas. They use epsilon, and there's machine learning people who use alpha. Actually, I guess I could have used alpha. And I know what you mean. Epsilon is
epsilon small is good.
so here epsilon small is also good. It's high privacy.
No, I know. That's why you chose it. What I'm getting at is, right.
No, epsilon is kind of a funny thing to say. Yeah. Okay, so it's a basic tool in the literature, and but there are really two questions one could ask, and I think these are really first order questions, which is couldn't the noise be data dependent? Why be independent? So question one, and question two, why not some other noise distribution? I mean, why this? And that's really what this talk is. And we'll address both these questions, and we'll answer them in a fairly general context. So I guess I never defined what the optimal criterion here is. Like it depends on what we want to work with. You can always add infinite noise and everything will work. And then you can be data independent too. But so the point I guess is that you have to have some framework under which I can talk of optimalities. This then framework will be fairly general and it involves some cost. So here's how it is. I add noise, could be data dependent, but example of cost would be something like the amplitude of the noise or the variance. And in general, you can take any loss function L. As long as it is sensible, that means it's monotonically increasing. That means more noise means more cost. So just that. And these are all numbers, so I just take some kind of symmetry around the origin. So that's it. So you can work with any cost that's increasing as the noise increases, and I would like to minimize the average cost. Okay, so more generally, this is how it looks like. I said you might add noise as a function of the data itself. So really speaking, there's actually a sequence of noises, one for each data value. And these random variables xt are related through the differential privacy, so they can't be whatever they want. So neighboring random variables should be related in some way. And I'd like to minimize the cost. Well, what cost? I said average one. But for which output? Well, let's just take the worst case. So I take the worst case average, worst case cost, and average. I look at the average of the worst case cost and I minimize it over all possible mechanisms. If you had some prior on the data, then I suppose you could have considered, instead of the worst case, you could have considered the average over that prior also. That's also a possible formulation.
So the entry that's answering the queries knows both databases? I mean, that's not necessarily.
No, so that's a good point. He doesn't. He just has this constraint in mind. He just knows that if they are neighboring databases, then I know my random variables have to be close by somehow. They can't be, they have to be correlated. They can't be independent because that would, neighboring things can get distinguished now. So this is the setup. So now it's a formal setup. It's parameterized by this loss function L. Potentially you might get different answers for different L, and that would be a bummer. Then it's not as exciting if we did, but yeah, that's the interesting part. Okay. Yes, Andre.
This xt is xt1 formula, probability of x.
Yeah, actually, I'm sorry. This is really, yeah, this is T1. Perfect. Thank you. Yeah, it's actually T1. Thank you. Our first result is the following. First result says that it's okay to be data independent. So every random variable is fully correlated as long as the domain that I'm talking about doesn't have sharp boundaries. If you think about it, if there's a sharp boundary, that means I'm limited to be between -1 and 1. When I say something near -1, then that kind of reveals a lot. You really could not have had too many things that get to that boundary. And then you have to be data dependent. So as long as you don't have any boundaries like this in your domain, you don't have this. Examples would be like a real line, if you have a lattice structure, like integers, or you have some nice compact group structure, subspaces, things like this, that would work, angles, things like that would work well. Like a Grassmannian or Stiefel manifolds work very well. So that's our first result. So you can be data independent. And furthermore, the second one is that the optimal noise is not Laplacian. It's got this shape. We call it this staircase shape for, I guess, staircase reason. And we call it the staircase mechanism. And the way to think of it is that it's really uniform random variables, but a geometric mixture of them. It's a geometric mixture, so it's decaying geometrically, but it's a geometric mixture of uniform random variables. And this is true no matter what the loss function is, as long as it was monotonically increasing in noise. So more the noise, the more the loss. It's a universal result. I should be precise. So this is how the staircase looks like. It's decaying geometrically, the height decaying geometrically. They're all of length, some lengths. And there is this parameter called gamma. So if you notice the colors were somewhat different, and it's because of this term called gamma. What is gamma? The gamma tells you when you jump from one to the other. And it's a number between 0 and 1, and that is not universal actually. That depends on the cost function. So for amplitude you'll pick something, variance you'll pick some other thing, but it's always between 0 and 1. So you might have to tune that. So the staircase shape is optimal, universal, but the gamma is not. So you might have to tune it. So that's kind of part of the result. So this was really a functional optimization problem, and this is the sort of the answer to that functional because it's PDFs or distributions in general. Yeah, one can quickly see that you don't want to do any discrete stuff. It just has to have a PDF, and that's not hard to see. So this is what it looks like. So let's see. So the other thing is that this might look like, I don't know, it looks like quantized Laplacian or something. Maybe it's not worth it anyway. But maybe it's just a modest technical result. So it's just, I guess, I'm guilty of having done that in the past. But the good thing is that it actually has a very big difference in how it works. So let's look at the example when the cost is just the magnitude. So like the kind of the first moment. Then, so you can solve exactly for gamma. It looks some number like this, between 0 and 1. You look at the cost, it looks something like this. Compare it with the Laplacian. When you compare it, when very high privacy regime, actually the Laplacian is near optimal. No problem actually. The gap is goes to 0. So Laplacian is doing already well. It's not too bad, very high privacy. But at low privacy, well, epsilon is large, 10, then it looks like 1 over epsilon, but this looks like e to the minus epsilon. So low privacy costs exponentially less than the state of the art if you use the right mechanism. How about, so you can look at numerically too. You have this exponential change at some point in epsilon. It switches around 5 or 6 and then it just goes into the exponential. It's initially kind of very flat for up to 1.5 and stuff like that, and then it just switches into the exponential mode. How about this variance? This is also a useful metric. And you can solve for gamma. It's kind of a pain, but this is just single parameter optimization. How hard can it be? You just solve it by hand. Solution to some polynomial equation. This is quartic actually. It's a quartic solution. More than higher order, you can still solution to some polynomial equation. For variance, it's a quartic, so I solve it by hand. You can calculate the cost. Everything is closed form. But the important point is that at low privacy, variance in state of the art looks like 1 over epsilon squared. Variance with the optimal one is e to the minus epsilon.
But the count query is epsilon upper bounded by 1 or something?
No, I'll talk about it. Count query is a very interesting example. I'll come to it. One more slide.
What about low privacy in this case?
No, epsilon is large.
No, high privacy.
High privacy, again, the gap is always non-zero, but they're bounded. And the ratio goes to 1. I'll come to count query, just 2 more slides. That's an important case. These I'm doing real numbers. Count queries are integers. So I'll come to the integer case just in a minute. Yeah, so you can again see that exponential behavior happening at some value of epsilon, it just kicks off. So this gamma is in general a sort of an annoyance because you have to find this number between 0 and 1. For every cost, you have to kind of tune it. Turns out we might have some answers in the sense that if you tell me epsilon is very small, then I say go ahead and pick half. If it's epsilon is kind of large, then I say go pick 0. And in general, I even have some universal choice. We can prove some properties that for every cost function, this choice has some minimally good properties. It can't be too bad.
So if I understand it, so when epsilon goes to 0, the size of these steps remains constant, but it becomes...
Yeah, when epsilon goes to 0, basically you are adding too much noise, and both the Laplacian and staircase are becoming like uniform. But small height, but really large noise. They're both becoming more and more like uniform noise. And at that point, actually, there are many noise distributions that all do well. You don't have to pick Laplacian. Even just uniform noise will do pretty good. You're just putting uniform over a large. Yeah, epsilon small is a relatively easier And the limit is easy to understand. You just have to add a lot of noise, and any reasonable way to do it will work. Yeah. So result is sort of canonical in the sense that, like I said, Laplacian mechanism is used in a bunch of papers, pretty much every paper. And in all those papers, actually we found 2 papers in where it doesn't, but in every other case you just kind of plug and play. Just remove that Laplacian foot staircase, strictly improves the performance. Sometimes it's marginal improvement, particularly in the high privacy cases, but sometimes it's a significant improvement. So here's one example.
Was there a reason people used the Laplacian before? That everyone used this?
Actually, I'm not. It's reasonable. See, it's the privacy constraint exactly because there is e to the minus epsilon there, and take the ratio. It fits nicely. It's not bad. Also, at high privacy, it's reasonable. Beyond that, I don't know. Actually, it's a good question. There's another reason, maybe I'll say when I come to count query. It's actually the optimal one. So sometimes, like I said, the performance is dramatically more. Here, and this is a very fast-moving area. There are lots of papers by the week and month. So here's one paper where they were trying to do distributed, like a graph, right? David has worked quite a bit on it early on, where each entry in the graph has a number, and they all want to agree on some other number. They want to get consensus. And a classic way is sort of gossip. Each person sends along their number, or they take an average of what they heard, weight it with what they had, and send it along, and eventually sort of, depending on the mixing time, you'll converge at a certain rate. So this is consensus. But suppose you want to do it privately. That means you all want to agree on a number, but you don't want, I as a node don't want anybody else to know what number I started with. So I'm going to add, whenever I say something else, I'll say noisily. So, but over time, when I send the average, I don't have to add so much noise. So you can try to do it privately. You will converge, but you won't converge exactly. So the consensus is still off, and the accuracy looks like 1 over root n. There's a constant that depends on the conductance of the graph and so forth. But this is a paper of Huang, Mitra, and Delarue, and n is the number of nodes in the graph. Assuming, again, they were using Laplacian mechanism. You go and replace the staircase mechanism there, and the accuracy just becomes like this. So that's the kind of application you can do of this work. So this is a setting that I was working only on real valued data so far. I've been working on real valued data, but of interest is also these things called discrete setting, where what you release is sort of an integer. So count query is a special case where the sensitivity is exactly 1, where 1% or not just changes the value by 1. In this case,
sorry, count query means what? Put in the database for what? Sites?
No. Yeah, one would be the example. Basically, whenever you say histogram, like you say how many people are above this number, let's say. Okay. And now 1% or not, it will only change at most by 1. Either it changes or it doesn't, and then it's only by 1. So in this case, and you only do integers. So this is kind of very minimal privacy requirement because you only want to change the value by 1, and you want to hide 10 from 11 or 9. That's all you want to hide. So very minimal privacy requirement. And there, Ghosh, Roughgarden, and Sundararajan in a 2009 Fox paper showed that a discrete variant of Laplacian, the geometric noise, is optimal. That's all there is. Because you just go to your neighbor, you decay as fast as you can. There's a minimal rate of decay, and that's it. And this is true in a universal context, no matter what the cost is. They were working they put a prior, and they were doing the average cost. So this is a 2009 Fox paper, and there it's exactly that. But turns out if it's not a count query, let's say, it's an integer nevertheless. Let's say sensitivity is 5 or something, it changes up to 5. Or maybe you had a finer quantization and the sensitivity is 5, then geometric is not, or Laplacian is not optimal anymore. There you need to do a discrete version of this staircase. So to answer Chandra's question, even when delta equal to 1, epsilon is interesting. It can be any epsilon. It's okay. But for count query, actually, state of that was already good. And it's shown to be good already. So this is, our results can be viewed. I guess we also did a result for discrete. And our discrete result can be viewed as a strict generalization of Ghosh, Roughgarden, and Sundararajan's Fox paper. And there are more abstract settings. So like I said, you might be releasing subspaces on this manifold. and the sensitivity is more some kind of an angle or something. You take the inner products and take something like an angle. And there's something called the exponential mechanism by McSherry and Talwar, which is like a Laplacian but just in abstract setting. So you can replace it directly by the staircase mechanism, improving each performances. Okay, so that's one type of generalization. Another generalization comes about where I don't release a number, but I release a whole vector. So I could have many queries, really, and what I release is like a vector. You can think of it as a vector I release. And sensitivity could be, so example would be a histogram. This is a very important example, where I release how many people are between 0 and 10, how many people between 10 and 20, 20 and 30, like that, like bins. And I say how many are in each one. So that's the statistical data release. Sensitivity depends on how much things change, and for histogram particularly, like I said, it was just 1. But you're releasing a vector this time. So now you have to add noise, but it's a vector. So for the histogram problem, turns out, so state of the art was adding kind of Laplacian noise independently. Though people knew in the literature, you can see that people know that you should correlate the noise, color them, because the sensitivity is colored. But the coloring was done in somewhat heuristic ways. Not clear. It beat the adding Laplacian in some way, in some regimes, but some it didn't. So it's kind of heuristic. Turns out the optimal one looks like this. Still staircase, but the uniform is now over L1 balls for concentric L1. L1 because I chose sensitivity in the L1 way. So this is L1. Yeah, we haven't, L2, I suspect it's also L2 balls, but the proof hasn't gone through yet. So that's sort of the kind of a result I have to say. There's one more thing I would like to say, and this is somewhat technical, and for people in the area, there is something called approximate differential privacy. So this is also proposed in the early work, very early work of 2005 by Dwark and her co-authors. And it involves not only epsilon, but also this parameter called lowercase delta. It's some kind of a generalization. If this lowercase delta is 0, then you're back to original definition. More generally, it's a little bit looser version. It just loosens, relaxes the condition, you can say. And with epsilon, in other words, if you put little delta equal to 0, then you're back to the usual definition. And so you want to think about epsilon 0 but delta. That's interesting case. I didn't see too much study in the literature, but it seems interesting mathematically to me. And that's just the total variation distance between the conditional measures. So you have two measures, and you would like the total variation to be something like this. So that's what the 0 delta is. And in general, you have something that covers both. So this is called approximate differential privacy. It's been around. You'll see a fair amount of literature on it. I don't know what the operational significance is. Epsilon 0 had a nice meaning, false alarm misdetection. This one I'm not sure in the hypothesis testing context. If you put some conditions, what it means on the false alarm misdetection. And somewhat unclear operational significance, but the state of the art is to add independent noise and Gaussian with a certain variance. This was also in the original work, and it's done in high dimensional settings, and this is the sort of the state of the art. So here's our result. In general, epsilon delta is more general than these two corner cases, for sure. It's more when I say more general, I mean it's looser notion of privacy than these two cases. These two are more stricter, and also potentially cost more. Turns out, not so much. At least for L1, L2 cost functions, that means amplitude and variance of the noises you add, there's really nothing much more to be done with epsilon delta than this or this. So in other words, the optimal mechanism, we don't know what it is, but whatever it is, it's no worse than, not by much at least, than the better of these two things. So we can, I guess the point, is that at least for L1, L2 cost functions, instead of working with epsilon delta, I just get even better privacy with hardly any extra cost to pay. Since the setting is somewhat fragile in some sense. That's what this result sort of says. At least for these cost functions, it's a little bit fragile.
What is the C-book?
So for L1, depends on the value of epsilons and deltas. With the limit when epsilon delta becomes small, very high privacy, this ratio of this and this looks like 1 for L1. And for L2 cost function, it looks like 5.32. So they're sort of small numbers. In fact, the ratio looks like 1. It's nearly optimal in the high privacy regime. So it's really nothing at all than the corner cases in the high privacy regime for L1. And for L2, it's 5 or something, 5.32. There are some form numbers for these things. Okay, let me summarize. So privacy is sort of a pressing matter. It's kind of hard to avoid. You look at the New York Times, New Yorker, anything, any popular articles, you'll see an article on privacy somewhere. There's sort of commercial interest. And it's kind of interesting in the sense that it's a complicated thing. It's got personalities involved, people's choices, it's got regulatory aspects, there's commercial things, societal, it's kind of a complicated thing. There's no one clear solution. And the ultimate protection is to sort of randomize. So systems work in this area is interesting. I have not done any yet. I'm still finding my way around. But there's efforts for sure. It's a pressing matter. The criticism about differential privacy really is that it's kind of impractical. You get high privacy guarantees, but it's worst case and you add too much noise, and then, as Mayank said, for health record, I mean, really, is privacy that important? You really want to do some stuff. Why are you adding noise? And one thing I'm trying to say, if you want to take away something, is that moderate to low privacy, maybe the cost is not much at all. You just have to do the right mechanism, though. In that sense, that's the sort of the take-home point here. If you do the right mechanisms, the price to pay is not much, maybe. High privacy, there's still a price to pay, but moderate to low. So that way you get a feel for a given cost, where you'll operate. If you are in the mood to pick, instead of picking privacy or not at all, maybe you'll pick moderate or low. From a statistical point of view, if you want to think about it, what we are deriving is some kind of a converse to Neyman-Pearson. So Neyman-Pearson is where you have a noise on your signal and you do the best rule, like maximum likelihood. You try to do those kind of rules to minimize false alarm misdetections. We are doing the opposite. I tell you false alarm misdetection and I ask what should be the noise, that minimum variance noise that fits it, something like this. So it's kind of a converse results to Neyman-Pearson. That's sort of the statistical value to this type of a result. As Balaji said, this is with my very multi-talented student, Chuan Geng, and so joined for business school. Finally, I would like to acknowledge Professor Thomas Covert. I was counting, this is my 6th talk in this room, and actually 2 of the talks were upstairs, just up here. So this is my 3rd talk in this room, so I miss Professor Covert here. He was there in all the other 5 talks before me here. One single constant presence. So I hope you have found this result surprising.
Question?
Yes.
So, there's also this notion that if you do group testing, for example, I want to be private with respect to that I belong to a certain population that has a certain characteristic, and I don't want to even have that characteristic be known that it exists within this population. So it's not just about finding out that this is my identity, it's also about finding out that such a thing even exists in this population. And some people don't like even that. In Europe, for example, they don't want anyone to know anything about the whole neighborhood. Everyone is gang members, also just follow those things. Do you think you need to change it against group testing type hypotheses where you're finding...
That's of interest. Pairwise is already pretty strong. In some sense, if I cover every possible pair, then I kind of cover more. I was thinking of maybe multi-hypothesis covering.
Exactly, it's stronger. So if you
Pairwise covers everything.
But if you weaken it, then maybe you can actually...
You can get even, possible. Yeah. So if you have only multi-hypothesis to cover, not every pair, then maybe there is something more possible, not explored here.
So in practice, what are the loss functions that people care about?
Okay, so it depends on what people are using. So the practice is also a little bit, I'm interested in this. I'm definitely interested in doing systems work in this. And there are plenty of papers, some of them sort of serious, some of them not so much. And variance shows up a lot. You see variance a lot in most of them. It's a surrogate somewhere or the other. In the distributed consensus, I said accuracy was really directly related to the variance, standard deviation of the noise. Sometimes the KL divergence shows up. So that's recent work of Ducci, Jordan, and Wainwright. Just actually March this year.
We'll hear about it tomorrow. So.
Yeah, John is here, exactly. That's right. So variance, I think, is a very popular surrogate of the how much noise you added.
So the distribution that you characterized was very dependent on the particular loss function.
No, so that's the whole, actually the point I said is that it's not dependent.
No, but the gamma.
Yeah, but turns out I even gave you, did I give you the universal choice of gamma? Yeah. So this is not bad actually. It's near optimal. We could prove some things for all loss functions. It's not bad at all. I even have a choice for you. I have some idea how gamma looks like. This is a pretty reasonable choice. There's one corollary somewhere in the paper that says why this might be a decent choice. Yeah, I think it would have been a bummer if the distribution changed for every loss function. That would be a bit of annoyance actually. So one of the values, or maybe the aesthetically interesting values, I think hopefully practically, is that it's universal.
So perhaps a question is how this deteriorated about multiple queries. So this basically tells you that you have so much false alarm or misdetection for the one query, but then in practice part.
Yeah, so that's the vector case. So in practice, you want to think of more like multiple queries. You just bunch them all together and talk of it as a vector. Okay, so several things happen. First, when you do multiple queries, if each of them is uncorrelated, that means when one user is there or not changes each component separately, then you should add in noise independent on each query. I mean, there's nothing you can do about it. So if the query outputs are uncorrelated, that means the sensitivity is not related to each other. The separate sensitivities, then you have no choice. You really have to protect every one of them. Then in that case, the variance is just increasing linearly in the number of queries because you're adding independent each time. But if it's correlated, and many important applications do, then this looks like, actually in the histogram case, it looks like something like square root of the n is the number of queries. It looks like sort of square root n.
Yes, in practice, you have expected that all the databases are present. I feel like that pairwise you're expecting there's B1 is present and then the B2, which is the one variation of it is also present, and so on and so forth. You might sort of own IMDb database and then you might test database and maybe some other new database.
No, I think even within the, yeah, I know what you mean. So in this case, I'm not actually, well, I guess in that case, you want to think about releasing the database is not, I guess I'm not, D1 and D2 are not sort of that kind of database. This is just instances of the database.
Correct.
So so you want to think of when I release statistical information, let's say I have some salaries and I release the average value. So the person he knows the underlying vector. He just doesn't know whether Devrath is involved in the vector or not. So it's a little bit like that's the anonymity.
So month to month salary data, as you were saying. If I know someone joined,
I guess this is an objection is if you have a prior Q of D, you know that Q of D is only prime numbers because salaries are only prime numbers. Then you can protect your add variance, your Q of D is literally 1, delta is 1, but you add noise basically of size 1. But if you see, 18, you know that it's 17, right? I think it's a common practice.
Yeah, so if you put, actually I must say our results are somewhat specialized only for these kind of domain. I should say it somewhere here. Yeah. So only when there's some structure, you can say some things. Otherwise, you have privacy mechanisms that are tailored to the scenario. So I'm really saying only things for some lattice structures from symmetry like this. Otherwise, I think it becomes you can do things that are tailored to the situation.